So in the last lecture, we have seen the basic properties of eigenvalue and eigenvector. Again, so eigenvalues, we are familiar with how to write the equation, characteristic equation, and then how to find it 3 by 3 matrix using a shortcut method, as well as we know about the Cramer's rule now, and we know how and when to apply this Cramer's rule. Okay, so now we'll try to solve some examples based on eigenvalues and eigenvectors, how to calculate the eigenvectors. Okay. So let us see. I hope you are able to see this Jamboard. Are you able to see the Jamboard?
Yes, sir.
Yeah.
Yes, sir.
Okay, that's good.
Yes, sir.
So many of you have already joined it. That's very good. Okay.
Excuse me, sir. Can you please share the link again of the Jamboard?
Jamboard. Okay.
Yeah.
Actually, you might have also got this in your mail. Okay.
Oh, okay, sir.
So
I'll check
the
it.
link also goes to mail. I'll also share it here. Okay. So I'm again shared.
Thank you,
Okay.
sir.
Yes. So I have shared it again. You can use this link also, or you might have got into mail. That also you can use this link and join the Jamboard. Now I hope you are all able to see this, right?
Yes, sir.
Yes, sir, it's visible.
Okay, that's great. Okay. Okay, so now we'll try to solve the problem based on the eigenvalue and eigenvectors. So we go with the example. Again, find the eigenvalues and eigenvectors again of the following matrix. Okay, so you can have this. So I hope you are able to see this example.
Yes, sir.
Are you able
Yes,
to see
sir.
this? Yeah.
Yes, sir. Yes.
Okay. So we have to find the eigenvalues and eigenvectors of this matrix. So this is the matrix given to us. Again, now you can see the matrix. The matrix A is 4, 6, 6, 1, 3, 2, -1, -5, and -2. Okay, and now we want to solve, or we want to find the eigenvalues and eigenvectors of this matrix. So we can have let A is equal to, okay, so always write the given things. So we have this is 4, 6, 6, 1, 3, 2, be careful, -1, -5, and -2. Okay, so B, the given matrix. Okay, now if I want to know the characteristic equation of this, what we know the characteristic equation, it is 3 by 3 matrix, so it is lambda cube minus S1 lambda square plus S2 lambda minus determinant of A is equal to 0. Okay, so what we got here, we want to find out determinant of A, we want to find out S1, we want to find out S2. Okay, so if I want to find out this S1, easily I can get it from here. S2 is the sum of minors of the diagonal elements, and then how we get this minus by using the determinant. So first we have to find out what is the determinant. Okay, so let us try to find out the determinant. Then what I'll write here, consider determinant of A. So please be careful where we have to write matrix and where we have to write determinant. We need to be very careful. So this is 466, 132. This is -1, -5, and -2. Okay, so I want you to use your calculator and then get this determinant. So please use the calculator and get the determinant. So what is the value of determinant we have?
So 4.
You have to find out the value of this determinant.
Sir, the value is coming out to be 4.
4. Okay, what about others? Please verify. Others have calculated this value or not yet?
So it's
Please
4.
calculate the value and get it.
4.
So
4.
4. Okay, fine. So we got the value of the determinant is going to be 4. Okay, and now I want to guess what are the eigenvalues. Okay, what will be the roots of this polynomial or this equation. Okay, so what I have to do is, I know the product is going to be 4. So what is the sum here? What is the sum here? What is the sum of the eigenvalues? The sum of the eigenvalues is nothing but the sum of the diagonal elements. Okay, so check this diagonal elements. So this is the diagonal element, this is the diagonal element, and this is the diagonal element. So what is the sum of these diagonal elements?
5.
5. Okay, so what I know is, I know sum is going to be 5. Okay, and product, okay, is going to be 4. So can you factorize this 4 such that the sum will be 5? Okay, and product is 4, so that means all the numbers we have to be non-zero. We have to consider the non-zero numbers with the product 4. So can you factorize this 4 into 3 parts, because this is the 3 by 3 matrix, so you will have 3 eigenvalues. So can you factorize this into 3 parts?
2 into 2 into 1.
2 into 2 into 1, and the sum is 2 plus 2 plus 1, so 5. Yes. Okay, so this is how you can get. So these are the eigenvalues. Okay, so easily without calculating actual eigenvalues, we are able to guess what will be the eigenvalues. Okay, and now we will check whether we have got it correct or not. And now we'll calculate this eigenvalue. So eigenvalues will be 2 to 1. Okay, or we can say 1 to 2.
Sir,
Yes.
can you explain the sum and the product again?
Yeah, no problem. But what is the relation between the eigenvalues and the product? Yes. Yeah, please. I have given you the comment. Okay, whose query was that?
Sir, mine.
Shivam. Okay, that's good. Okay, so Shivam, we have a property of eigenvalues. Okay, so which relates the product of the matrix and the trace of the matrix. Trace is the sum of diagonal elements, which is called trace. Okay, so we need to understand what is the relation between these two. Okay, so can you tell me what is the relation between the product of eigenvalues and the matrix? Yes, Shivam.
So could you repeat?
What is the relation between the product of eigenvalues and the matrix?
Sum of diagonal element.
I am talking about the product of eigenvalues.
So that's equal to the determinant of the matrix.
Yes. Okay. So the sum of the the product of the eigenvalues is going to be the determinant of the matrix. Now, can you tell me what is the relation between the sum of the eigenvalues and the matrix? Shivam.
Sir, a sum of diagonal elements of a matrix.
Yes, very good. Okay, so these are the two things that we have to keep in our mind. Okay, the first thing is the sum of the eigenvalues is equal to the sum of the diagonal element, which is called as a trace of that matrix. And the next thing is the product of all eigenvalues is nothing but the determinant of the matrix. Okay, so using these two things, we are going to understand that. Okay, so let us try to understand what I did. Okay, so here we have, see, the sum is going to be, so what I can have is I have the trace of matrix. So trace, so trace of A. Trace of A means the sum of the diagonal elements. So it is going to be 4 plus 3, okay, plus 3 minus 2, and so it is going to be 5. So trace of A is equal to 5. Okay, and we know this is what you will be having, sum. So it is sum of eigenvalues. Okay, so sum of eigenvalues we got, that's going to be 5. And now what about the product we know? Okay, so the product of the eigenvalues is nothing but the determinant of A, which is equal to 4. Okay, so now we have to factorize this 4 into 3 parts. Okay, so we have to factorize this 4 into 3 parts such that the sum is going to be 5. So Shivam, can you factorize 4 into 3 parts such that the sum is going to be 5?
Yes, sir.
Yeah. So can you tell me what will
Sir,
be
2 into 2 into.
the factors of this? Correct. So this is going to be 2 into 2 into 1. So it is 2 plus 2 plus 1. Sorry. So it is going to be 2 plus 2 plus 1. Okay. And this is how these are going to be the eigenvalues. So 1, 2, 2. This is the first guess that these are going to be the eigenvalues. Okay. And now we'll see whether we get these eigenvalues actually or not. So Shivam, have you got your queries satisfied?
Yes, sir. Yes, sir. Solved. Yes, sir. Satisfied.
Okay. Yes, that's important. No need to say sorry. It's okay. Okay. So you got your query now, correct? Okay. So once we got this, okay, now we need to show the calculation that whether we are able to get the same or not. Okay. So if I say we have the characteristic equation of the given matrix as this is determinant of A minus lambda I is equal to 0. Okay, and now let us have this. Okay, so what we got here, determinant of A. So it is 4, 6, 6. Then I'll be having this is 1, 3, 2. 1, 3, 2. And then this is minus 1, minus 5 and minus 2. Minus 1, minus 5 and minus 2. And we want this has to be 0. But then minus lambda I. So minus lambda you will have here. Okay. So you can see what we got is determinant of A minus lambda is equal to 0. Okay. So determinant of A minus lambda is equal to 0. Okay. And what we know is we know the shortcut, that is lambda cube minus S1 lambda square plus S2 lambda minus determinant of A is equal to 0. Okay, so that's what we have. Now let us write down this equation. So what this equation will be, lambda cube minus lambda square. Okay, and here you will be having 4 plus 3 minus 2. Okay, S1, the sum of diagonal elements. So S1, what do you have? Sum of diagonal elements of A. And what is S2? S2 is sum of minors of diagonal elements. Okay, so that's what we need to understand. Okay, so we got here, this is going to be the lambda cube. Okay, so we got here lambda cube minus lambda square, sum of the diagonal elements. So it is going to be 4 plus 3 minus 2, and then minus, this will be plus lambda times. What is the next S2? S2 is going to be the sum of the minors. Okay, so what are the minors you will be having? So this 4, if I consider the first element, then I'll be having these 4 elements will be the minor. So what you'll be having, 3 2s are minus 6, and then you'll be having minus minus plus, and then this term is going to be plus 10. Okay, so this is the value of the determinant, 3 2 minus 5 and minus 2. So 3 2s are 6 minus 6, and then 5 2s are 10, with the minus sign, again minus minus becomes plus. Then next, okay, so what do we have the next? So the next minor is for this 3. Okay, so what will be the minor for this 3? So we'll be having 4 6 minus 1 minus 2. Okay, what we got? Because for this 3 we have to omit this second row and second column. Okay, so it will be 4 6 minus 1 minus 2, and you can see what will be the minor here. So it is going to be minus 8 minus minus plus 6. Okay, that's what we'll be having, plus. And now for this minus 2, what will be the minor? The minor will be 4 6, and you will be having 1 3. Okay, because for this 2 we have to omit the third row and third column, and now you can see, so 4 3s are 12 and minus 6, and then minus determinant. So we have calculated the determinant, so determinant is going to be 4, and it is here. So we can have the determinant, okay, and that is going to be 4, and this is 0. Okay, so is there any doubt in this equation? You got this minus value?
Yes, sir.
Yes, sir.
Okay, that's good. Okay, so you got this minor value. Now let us simplify. Okay, so you will be having lambda cube minus, so you got here 5 lambda square, and then we have to consider here plus. So this is going to be 4, this is going to be minus 2, and this is going to be plus 6. Okay, so this is going to be 4, this is going to be minus 2, and this is going to be plus 6. Now we have lambda, and then minus 4 is equal to 0. So we got the equation lambda cube minus 5 lambda square, and how much is this going to be? Plus 8 lambda, and this is minus 4, and is equal to 0. Okay, so this is the equation that we got. And now I want you to use the calculator and then find out what are the factors. So don't tell me the roots, but please tell me what are the factors you can have. So factors will be of the form lambda minus A, okay, lambda minus B, lambda minus C is equal to 0. So this kind of factorization I want, because I have 3 roots here. So this is a cubic polynomial, so I'll be having 3 roots. So I want you to find out these 3 roots by using the calculator directly. So can you please tell me what are the roots you are getting, or what are the factors you are getting? What are the factors we have here? Are you getting it? Use your calculator and then get the values. Anyone of you got it?
Lambda minus 1, lambda minus 2, lambda minus 2
Yeah.
equal to
Okay.
0.
So it is lambda minus 1, lambda minus 2 bracket square is equal to 0, because this is coming 2 times. Okay. So we can say lambda is equal to 1, 2, 2. Okay. So though it is repeated, we have to write it 2 times, and hence I can say that the eigenvalues of A are 1, 2, 2. Okay, so these are the eigenvalues. Okay, so once you get the eigenvalues, the next task is to find out the eigenvectors. Okay, so let us try to find out the eigenvectors. Okay, so what we'll be having for lambda is equal to 1, the first eigenvalue. Okay, so we have eigenvalue 1, then eigenvalue 2, and this 2 is repeated. So let us see what happens to that. Okay, so for lambda is equal to 1, we have to be careful, and then we always have to write a minus lambda I into x is equal to 0. So please be careful. Here what we have used the determinant a minus lambda I, and here what we have the matrix a minus lambda I and is equal to x into x is equal to 0. Okay, so this x we have to find out. So we have to find out the vector x such that the action of this matrix on this x gives you the answer 0. Okay, so that means we have to find out, we have a matrix a minus lambda I, and then we have to find out this vector x such that this goes to 0. This is 0 means it is a vector 0. Okay, so this goes to 0. So our task is to find out this. Okay, so we have to find out the direction in which this control is working. Okay, so we have to find out the direction in which this control lambda, the eigenvalues are the controlling points. Okay, and the vectors are the direction of that control point. Okay, so we have to find out the direction of this control point. Lambda is equal to 1. Okay, so we have to find out the vector such that this matrix will take this vector to 0. Okay, now here when we say capital X, it is going to be the vector, small x is going to be a component. Okay, so now we write here, okay, what do we have? This matrix, and then the value of lambda is going to be 1 now. Okay, so the value of lambda is going to be 1. Okay, so if I consider here, so it is going to be 3, 6, 6. Okay, so this lambda is going to be 1, so this will be 3, 6, 6. This will be 1, 2, 2. Okay, so we got here 1, 2, 2. Okay, now next, so it is minus 1, minus 5, and this term is going to be minus 3. Okay, so minus 1, minus 5, and we got here this is going to be minus 3. Okay, and then we write this vector with the component x1, x2, x3. Why x1, x2, x3? Because our dimension is 3 dimension. So our vector, this matrix is 3 cross 3. That's why we have the 3 components. And here you can have this is going to be 0, 0, 0, all 0 vector. Okay, and now you can see this is the system that Ax is equal to 0. So we have to solve this system of linear equation. So we can solve this system of linear equation by rank analysis. Okay, so now can you tell me how many distinct equations you can see? How many distinct equations you can see in this matrix?
Okay.
How many? 1, 2, 3, 4. These are the different options. So can you tell me how many different equations you can see?
That's 3.
3 different equations.
Different equations you can see. So I'll write these equations. Okay. So what this system represents. So I'll write the equation 3x1 plus 6x2 plus 6x3 is equal to 0. Then x1 plus 2x2 plus 2x3 is equal to 0 minus x1. Okay, so minus x1 minus 5x2 minus 3x3 is equal to 0. So these are the equations represented by the system. It is in terms of matrices. This is in terms of the polynomial equations. So can you tell me how many distinct equations you can see? How many distinct equations you can see?
3.
3 equations. Okay. So let us divide this equation by 3. So you get x1 plus 2x2 plus 2x3. Now can you tell me how many distinct equations you can see?
2, 2.
Because this is same as this one, no?
Yes,
Isn't it?
yes, sir.
This equation is same as this equation. So there are only two distinct equations. Okay, what you can have is there are only two distinct equations. And you know, if I have two distinct equations with the right hand side 0, what I can do is, which rule we can use?
Cramer's rule.
Yes. So here Cramer's rule is applicable. Okay, because you will solve this, you will reduce the rank, and then you will see that the rank is going to be 2, and then you will try to reduce it, and then again using the back substitution you will be able to find out the solution. Okay, but before that we can just find out how many distinct equations I have. So if it is less than, if it is 2, then Cramer's rule is directly applicable. Okay, so here we got there are two distinct equations. Precisely we can say the second and third row, because first row is a scalar multiple of this second row. Okay, so there are only two equations, the second row and third row, and that's why the Cramer's rule is applicable. So we can say directly by Cramer's rule, we get. Okay, so what you are able to get is x1. So here the components are x1, x2, x3. So we have x1. And now when you write x1, that means we have to omit the column of x1. Okay, so it becomes 2, 2, minus 5 and minus 3. And then second component is minus. So x2. Okay, and here what will be having? 1 minus 1, 2 minus 3. Then the third component x3. Okay, so what will be having? 1 minus 1 and 2 minus 5. Okay, so this way we are able to use the Cramer's rule for the last two equations, and then we are able to get this. Okay, so what we get here, x1. Solve these determinants. So we'll be having this is going to be minus 6 and plus you can have 10. So it is minus x2, and here you will be having minus 3 plus 2. And here this is x3. So we'll be having this is minus 5 and plus 2. Okay, so you can see what we are able to get is x1 by 4 is equal to, this is going to be minus 1. So already we have minus. So x2 by 1. And here we can have, this is x3 by minus 3. So this way we got the x1, x2 and x3. And so we can write here the eigenvector is given as, so what you will be having, the first eigenvector. So it is going to be 4, 1 minus, you can say. Okay, so what you got here, 4, 1 minus 3. So it is going to be 4, 1 minus 3. Okay, so this is going to be the eigenvector. So now this is actually the equation of the line, and these are the direction ratios of the equation in that particular direction. So x1 by 4, so 4 is the direction ratio in x1 direction, x2 by 1, so it is 1 in the direction of x2, and it is minus 3, so it is minus 3 in the direction of x3. So using these 3 points we are able to locate that plane particular. Okay, so here we got the eigenvector. Okay, so we have the eigenvalue, and then we got the eigenvector. So the eigenvector is given as x1 is equal to, and this eigenvector is corresponding to eigenvalue lambda is equal to 1. And now we have to think of for lambda is equal to 2. Okay, so we have to do the similar calculation for lambda is equal to 2. Okay, so again we start with, okay, then we have a minus lambda I into x is equal to 0. Okay, so always start for what value, what eigenvalue you are finding the eigenvector, then how you are going to find the eigenvector. So again, here we need to understand this construction. So it is 4 minus 2. Okay, so we got here this is going to be 2. Then this 6 remains as it is. So we'll be having 1. Now what we got here, 3 minus 2. So if I consider 3 minus 2, it is going to be 1, and this is going to be 2. Now next you need to think, this is minus 1, minus 5 remains as it is, and this will become minus 4. Okay, so you got here this minus 1, this minus 5, and this is going to be minus 4. And now you can see x1, x2, x3. So we got here all zeros. Okay, so how many distinct equations you have now?
3 distinct equation.
Whatever, how many distinct equations we have?
3 distinct equation.
Sir,
It is
3 distinct equation.
Yes. Okay, so if it is 3 distinct equations, we don't have any problem. Okay, because we don't have to decide which equation to leave, no? So here Cramer's rule is applicable, as we require minimum 2 distinct equations for the Cramer rule. So here Cramer rule is applicable, and hence you can choose any 2 equations. So you can choose 1 and 2, you can choose 1 and 3, you can choose 2 and 3. So any of these 3 combination you can choose. Okay, so which one you want to choose? First, second, or third? First. Okay. Always mark that what you are going to take. Okay, so it becomes easy for you to write the determinants. Okay, so here we have considered this first 2 equations. Okay, so what we can have then, we have, again, so we get by Cramer's rule. So what do you have by Cramer's rule? So you can have x1 upon. Okay, so when I consider x1, that means we have to remove the first column and first row. Okay, so this is the value of the determinant. So it will be 1, 2, minus 5, minus 4. Okay, so x1, what we got here? This is going to be 1, 2, minus 5, 1, 2, minus 5, minus 4. Then this is equal to minus x2. Okay, so for x2, what we have to do is, we have to remove this second column. So we can have 2, 6, 1, 2. Sorry, here we need to check this minor. Okay. We have to consider within these 2 equations. So within these 2 equations, what will be 6, 6, 1, 2? Okay, this is 6, 6, 1, 2, and this is equal to, what you will be having within these 2 equations, 2, 1, 6, 2, 2, 1, 6, 2, and now x3. So what do you have x3 here? So this is 2, 1, 6, 1. Okay, 2, 1, 6, 1. Okay, because we are using Cramer rule, so we have to consider first 2 equations only. Okay, now let us have it. So x1 by what you can have is 6, and this is minus x2. So what do you have here? 4 minus 6. Okay, this is equal to x3, and you can have 2 minus 6. So what we got here? This is x1 by 6 minus x2 by 2 and x3 by minus 4. So what is the common that you can cancel out? Maximum common factor which you can cancel out.
Sir, in x2 there will no minus here.
Yeah, this will be minus. No? So minus minus can be cancelled, right?
Yes.
Okay, that's good. Okay, so what is the maximum value that you can cancel, or what is the common factor that you can cancel in this?
2.
2. So what will be having? X1 by 3, x2 by 1, and this is x3 by minus 2. Okay, so we can say the eigenvector corresponding to eigenvalue 2 is, so what we got here, x2, and that is going to be b1 minus 2. Okay, so this way we are able to get the eigenvalue for this matrix and for this eigen values. Okay, so here we got only one eigenvalue corresponding to this lambda. So though this lambda is repeated 2 times, so here we got the value 2, 2 times. Okay, so here the value of lambda is equal to 2 is repeated 2 times, but we can see we are able to find out only one eigenvector. So is there any chance that you will find out another eigenvector? So you can verify this answer. Okay, I have chosen the first 2 rows. Okay, you can some of you can choose the first and the third row, and some of you can choose the second and the third row, and verify this answer. Verify that you get the same eigenvector or not. Okay, so that's what you have to do. You have to verify that you get the same eigenvector or not. So is there any doubt in this example?
No, sir.
No, sir.
No, sir.
No, sir. No, sir.
All of you got this example?
Yes, sir.
Yes, sir.
All of you got this? Good.
Yes, sir.
Okay. So if you are able to get this easily, okay, that's a good one. Okay, so we can think of the next example then. Okay, so let us try to have the another example. So if you have any doubt, you please can ask. Okay, before we go to next example. If you don't have any doubt, then we'll go for the next example. So shall we go for next example now? Naveen?
Yes, sir.
Yes, sir. Go ahead.
Yes, sir.
Yes, sir.
Okay. So let us go for the next example. Okay. So we can think of the next example. So we have the matrix now. Okay. And then we have to find out the eigenvalues and eigenvectors for this matrix. Okay, and this question was asked in December 14 and May 16. Okay, so this is the university question. Now let us try to find out the eigenvalues and eigenvectors of this matrix. Okay, so what we should do first, let A is equal to, okay, so what we have, 2 1 1, 2 3 2, and then 3 3 4. Okay, so B the given matrix. Okay, then we have, so what will be having determinant of A. First, we want to find out the determinant. So you can have 2T2, T3, 4. So can any one of you tell me what is the determinant value?
7.
Is going to be 7. Okay, so you can get that the product of all the eigenvalues is going to be 7. Okay, then we consider the characteristic equation of matrix A. So what is the characteristic equation we have? Determinant of A minus lambda is equal to 0. So let us write this. So what we got here? We got 2, 1, 1. So it is 2 minus lambda and 1, 1 times this. Okay. So we got this 2, 1, 1. Now next. So what do you have? You have 2, 3, 2. So it is 2, 3 minus lambda 2. And then last, what you can have? 3, 3, 4. So it is going to be 3, 3, 4 minus lambda, and then this equal to 0. And we know the shortcut. So what is the shortcut? Lambda cube minus S1 lambda square minus S2 lambda, and then this equal minus A equal to 0. Okay, so this is the equation that we want to find out. So let us try to find out this. So what do you have here? Lambda cube minus. What is the sum of the diagonal element?
9.
9.
So it is going to be 9, 2, 3, 2 plus 3 plus 4. So it is going to be lambda, which is 9. So this sum is going to be 9. So minus 9 lambda square. Then plus. What you can have is lambda into the minus. So what will be the minor of this diagonal element? So for this 2, we have the minor 3, 4 and this 2, 3. So you got here. So this will be 12 minus 6 plus. Okay, think of the minor of this element. So you got 3, 2 and 4, 1. So what will be the value? So it is going to be 8 minus 3. Then next. Okay, so we want the minor of this 4. What will be the minor of this 4? So it is going to be 2, 3 are 6 and minus 2. And what is the value you got here? So determinant we have calculated, and that is going to be 7, which is equal to 0. Okay. So as in the previous case, what we know here, we know that sum is 7 and the product is 9. So can you factorize this 9 such that the sum is going to be 7? Sorry, the product is here. The product is 7 and the sum is going to be 9.
So 7, 1, 1.
Great. Okay. So this is product and this is sum. So you can have 7, 1, 1. So 7 plus 1 plus 1. So without calculating actually the eigenvalues, you are able to get the eigenvalues. So eigenvalues must be 7, 1, 1. Okay, and this is how the examples are used in competitive examination, or these are kind of problems that will be asked in the competitive examination. So just the matrix will be given, and then you will be asked find the product of the all eigenvalues. So actually you don't need to find out the eigenvalues, you just have to find out the determinant of that matrix, or the sum will be asked to you directly, or what may be the eigenvalues that you have to predict. So using these relations you are able to predict the eigenvalue, as well as you are able to find the product of the eigenvalue, and as well as you are able to find out the sum of the eigenvalue without calculating actual eigenvalues. Okay, so we got here, and hence simplify this equation. So what this equation is going to be? So this is lambda cube minus 9 lambda square. How much is this going to be? Plus, so it is 6 plus this is 5 and plus this is going to be 4 lambda minus 7 is equal to 0. Is that okay? Are you getting this one?
Yes, sir.
Lambda cube minus lambda square, then you'll be having plus. So what do you got here? So it is going to be 9 plus this is going to be 15 lambda minus 7 is equal to 0. Okay, so can you factorize this equation or factorize this polynomial and then get me the actual roots? So 711 was our guess. Now we have to see that they work actually or not. So use your calculator, solve this polynomial or solve this equation, and then you will get the eigenvalues. So what are the eigenvalues you are getting?
711.
Yeah. Okay. So we got here, this is lambda minus 1 bracket square into lambda minus 7 is equal to 0. So we got lambda is equal to 1 comma 1 comma 7. Okay, and hence we can say that the eigenvalues of A are 1, 1 and 7. Are you getting up to this? Have you got up to this?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Great, that's good. So now we got the eigenvalues. Let us find out the eigenvectors. So what we'll be having? Consider for lambda is equal to 1. So how we are going to find the eigenvector? A minus lambda I into x is equal to 0. So we have to solve this system of equations and then we are able to get it. So what we have here? A minus lambda I, and lambda is going to be 1. So let us use that. So from diagonal element you have to subtract 1. Okay, so it will be 2 minus 1. So it is going to be 2 minus 1, so it's going to be 1. Okay, so you got here 1 1 1, you got here 2 2 2, and you got here 3 3 3. Into we got here x1, x2, x3, and here we have this is 0. Okay, so can you identify how many equations we have?
Only one.
How many
Only one.
equations we have?
One.
Only one. Okay, so is the Cramer's rule applicable?
No, sir.
No. Okay, so this is the important thing that we need to understand. When the Cramer's rule is not applicable, what to do? Okay, because I want to find out a non-zero vector. So my task is to find out the non-zero vector, and hence to find the non-zero vector, we need to understand this one. So we have only one equation. Okay, and that is, so what is the equation? X1 plus x2 plus x3 is equal to 0. Okay, because this is 2 times this and this is 3 times this. So we have only one equation. And now we have to solve this equation, okay, for 2. That means I have to set one of them equal to 0. Okay, so what I can do is, without loss of generality, okay, we consider x3 is equal to 0. So this is case 1. Okay, so we need to understand case 1. So in case 1, what we are going to do is, let x3 is equal to 0. Okay, then we have x1 plus x2 equal to 0. So can I write this x2 like minus x1? Can we write it like this?
Yes, sir.
Yes. Okay, so we have the first vector. Okay, so x3 is equal to 0. Okay, so x3 is going to be 0. The first vector we are calculating. What you can have from here, x2 is minus x1. So if I put this one, this will be minus 1. Is that okay? Are you getting this vector?
Yes, sir.
x3 is going to be 0, so I have put this 0. x2 is equal to minus of x1, so I am assuming that x1 is equal to 1, so x2 becomes minus 1, and hence I can say this is the eigenvector corresponding to eigenvalue lambda is equal to 1. Okay, so this is the first eigenvector that we obtained. Now similarly we can set x2 is equal to 0. Okay, so we can have case 2. Okay, so what is the case 2? Let x2 is equal to 0. We have x1 plus x3 is equal to 0, and we can write x3 is equal to minus x1. So we can have the third eigenvector as, so we have this is 0 because x2 we have assumed to be 0, and what is x3? x3 is minus of x1. So if I consider this one, I have to write this as minus 1. So I can say is the vector corresponding to eigenvalue lambda is equal to 1. So here we got the two eigenvectors. Okay, then the question is why do we don't go for case 3 when lambda when x1 is equal to 0? Okay, so there is a basic thing that we need to understand. Okay, that there can be at the most, okay, at the most number of linearly independent eigenvectors where this number is equal to the number of times eigenvalue is repeated in characteristic equation. Okay, so we call it as the algebraic multiplicity. Okay, so the number of times the eigenvalue is repeated in the characteristic equation. Okay, that at the most that many number of eigenvectors you can have. And for this example, we can see that this one is repeated 2 times. Okay, so at the most it will be 2 times. Okay, so we can have at the most 2 eigenvectors. Okay, so is there any doubt in this? Is there any doubt in this eigenvectors? Nehanshu?
Sir, so for lambda is equal to 7, we don't have to calculate the value.
No, we have to calculate the value. Okay, we have to calculate. I'm just asking, is there any doubt? Because this is a repeated case, no? Okay, so if you are able to understand the repeated case, then non-repeated is very easy. Only we need to understand the repeated case, what to do when we have a repeated case. So you can see in the previous example, though 2 was repeated, but there was only one eigenvector. In this case, 1 is repeated and we have 2 distinct eigenvectors. Okay, so that's how this example is different of the different type from the previous one, and that's why I'm asking if there any doubt. Okay, so if you don't have any doubt, then we can go for the next eigenvalue. Okay, so let us calculate the eigenvector for the next eigenvalue. Okay, so we got the eigenvectors for this eigenvalue. So this was the first eigenvector. So this you can have the second eigenvector. Okay, so you can have second eigenvector. And now consider for lambda is equal to 7. So we have what we'll be having a minus lambda I into x is equal to 0. So now this lambda is going to be 7. So what is the matrix we have? See, we have 2 minus 7, so this is going to be minus 5. Okay, so you can have this is minus 5, and you'll be having 1 1. Then this is 2. 3 minus 7. So 2, 3 minus 7 is minus 4, and this is 2. Now 3 3 and 4 minus 7. So 3 3 and 4 minus 7. So it is minus 7. And we have here x1, x2, x3, and this is equal to 0 0 0. So how many distinct equations we have?
3.
Three distinct equation.
We have all 3 distinct equations, no?
Yes, sir.
Yes. So that means we can choose any 2 and we can apply the Cramer's rule. So which 2 you want to choose?
Second, third.
Second, third. Okay. So let us choose this second and third. So we can say by using Cramer's rule. Okay. By Cramer's rule. We have. Okay. So what we can have? See, we have x1. Okay. So second and third, it will be minus 4 2 and 3 minus 3. So minus 4 2, 3 minus 3. This is equal to minus x2. Okay. What we have here? This is 2 3 and 2 minus 3. So it is 2 3, 2 minus 3, and this is x3. So what we have for x3? It is 2 minus 4 3 3. 2 minus 4 and 3 3. Okay, so calculate this. What you got here? X1 by. So this is going to be 12.
X1 by 6.
X1 by 6.
6.
What about this x2?
Minus 12.
What it will be?
Minus 12.
Minus 12. Okay, and what about x3?
18.
18.
18.
Plus 18 minus 18
Plus 18.
plus 18. So do you find anything common that you can cancel?
3.
6.
6.
6 you can cancel, no?
6.
So it will be
Yes, sir.
1,
1, 2, and 3.
simple. Okay, and hence what you got is the third eigenvector is what? 1, 2, and 3. Okay, so we can say is the eigenvector corresponding to eigenvalue lambda is equal to 7. Okay, so this way we are able to get the eigenvalues and eigenvectors. Okay, and this is how we are able to use the Cramer's rule, as well as when Cramer rule is not applicable, we have to think of the other option. So when we have only one equation, what we can do? If we have 2 distinct equations, then what we can do? So is there any doubt for this lambda is equal to 7?
No, sir.
No, sir.
Okay, that's great. Okay, so this is how we are able to find the eigenvalues and eigenvectors. So here we have seen what happens if I have a repeated eigenvalue. Okay, if I have 3 distinct eigenvalues, then it is the easiest problem. Okay, so if we have 3 distinct eigenvalues, then 3 times you have to use Cramer rule and easily you are able to get the solution. Okay, but what happens if we have the repeated eigenvalues? Once we are able to use the Cramer rule, other time we don't we are not able to use the Cramer rule. Okay, so when we are not able to use the Cramer rule, that means we have only one equation. At that time we have to consider the different cases. Okay, now while considering the different cases, what cases we have to consider? Okay, so first we consider x3 is equal to 0 and then solve the equation. Then next time we consider x2 is equal to 0 and then solve the equation. Okay, and after solving this, why do we do not consider x1 is equal to 0? Okay, so the first thing that you need to understand is avoid using first component equal to 0. Okay, so you should not consider x1 is equal to 0. But in Cramer rule, if it comes x1 equal to 0, then we are ready to accept it. Okay, but we should not set x1 is equal to 0. Okay, the next thing is that if you consider x1 is equal to 0, then you will get a different vector which is actually orthogonal to the remaining two vectors. Okay, and that's why if I consider the three vectors, instead of considering only two for that eigenvalue, which is repeated 2 times, okay, then one of the vector will be the linear combinations of other two. Okay, so they will not be linearly independent. So how many vectors will be linearly independent? The number of time eigenvalue is repeated. So what we have, the number of time eigenvalue is repeated, that many vectors you can find which will be linearly independent. And if you try to find more than that, then the more vectors will be the linear combination of remaining two. Okay, so this is why we have not calculated the third eigenvector corresponding to lambda is equal to 1. Okay, so is there any doubt?
No, sir.
No, sir.
Okay, so that's good. You don't have any doubt. Okay, so if you have any doubt, you can ask, no problem.